Okay, so let's try to find an equation for the displacement and the slope for a simple supported beam with a load P in the middle. And this is the one, this is the first problem we've worked where you can see there's a change. What is the change? Think about the moment equation. Is the moment equation continuous across the whole beam? Can you write one equation for moment that varies from A to B? No. You can write an equation that's good from 0 to L over 2, and you can write a second equation that's good from L over 2 to L. They're different equations. So not only do we have to write two equations, all right, the way we do the integration will be different. Now, I don't think I have to do too much work and for you to get that the reactions are going to be P over 2 on both sides. You could do your statics and find that pretty quickly, but I want to try to get through this one a little more timely fashion. So let's try to write an equation for the moment that's valid from 0 to L over 2. So I'll make a cut in my beam, some distance x, and I have my P over 2 reaction. That's going to act as shear, and then I'm going to assume positive bending moment occurs there. And I'm going to call this bending moment, I'm going to subscript this I. That's the Roman numeral really 1. So I'm going to have a moment equation for what I'll call interval 1 and a moment equation for interval 2. Is this thing blinking again? Yeah. See if I can wiggle the... Is it blinking? Maybe it's... I think I may have the cable stretched a little too tight. Let's see if that works better. Okay, you can see that's not a hard... Look at that free body diagram. That's not the worst one you've ever worked. In fact, if you sum the moments using right-hand rule at the cut, make sure you have equilibrium, you can see you just have the moment that we're looking for, and then minus the force, P over 2 times x. So the moment in the first section is just Px over 2. And that's it. That blinked again, didn't it? Yeah.
Dr. Ivy used it the whole time and they never blinked.
It's just him. It doesn't like me. There's a ghost in the machine. Maybe it's one of my great uncles or something trying to get back at me. I was the bratty kid that would spill his beer or something. I don't know. So now we do. Yeah, so let's try this. I'm going to kind of split the page in half, and I'll come over here and we'll do L over 2 to L. So in this case, I'm going to go over a certain distance x, and then I'll have my cut. Still have the reaction on the right-hand side, P over 2. And now I'll have the moment, positive bending moment, in the second phase. Now we already know that if this is x, then this distance is going to be L minus x. So again, when I sum moments about the cut, I'm using the right-hand side of that cut. I'll have my moment at 2 creates negative moment, and then I'll have plus P over 2 times L minus x. So the moment in the second section is just going to be P over 2 times L minus x. Can we check these equations before we go any farther? Sure. Go to the first one. What's the moment when x equal to 0? Equation says 0, and we know that moment is 0. We also know the moment is 0 at B, which is at x equal L. I have to use this equation for that. So when I put in x equal L, what do I get? 0. So, is there another place to check these equations? L over 2. Mr. Driscoll's correct. So if I put L over 2 here, which is the limit of this one, I get PL over 4. Now if I put L over 2 here, I get what? Oh, I think I messed up here. No? Oh, that's right. L minus L over 2 is L over 2. You get PL over 4. So they match. So they not only match on the ends where you know it's 0, they match where they connect, L over 2. So that, I like that. So I think we're okay. So now let's go back and start integrating these things. So now I want to try to find the slope in the first section, which I know is the integral of the moment in the first section divided by EI. So this is a pretty easy equation to integrate. What is it? Px squared over 4. So that just becomes Px squared over 4EI plus an integration constant. Now, in this first section, do I know anything about the slope? Well, you don't know it from the end condition. Now, this beam does have an interesting thing that the load is symmetric, and you can have the insight that the slope at the midpoint is 0. So you could evaluate C1 right here by saying, oh, I know the slope at L over 2 is 0. But I'm not going to do that. Because if I shift this load a little bit left or right, that condition is not valid. So let's just do it in general. I just want to show you what you would be up against if you did that. So now the displacement in the first section is the integral of the slope. So I integrate this thing. So what do I get? I get Px cubed over 12EI plus C1x plus C2. But I do know something there. I do know the displacement at A is 0. So I can solve for something here. Let's just hold on to that for right now. Let's go to the other side and do the same thing. So what is the slope in the second section? Well, it's the integral of the second moment divided by EI. So let's integrate this guy. So again, we'll have P over 2 times Lx minus x squared over 2 plus another integration constant, C3. Okay? Then integrate. Do I know anything about the slope on this side? Well, I don't know it from the support reaction. Again, we've already discussed that we probably know that the slope is 0 at the middle, and we could apply that there. In fact, the author of your textbook says, well, that's true, that's how you solve this problem. But I want to show you how to do it in general. So, we'll just leave it like that, and we'll integrate it again. So what is the slope? So let's integrate this thing one more time. So I still got my P over 2 as a constant. So now I have Lx squared over 2 minus x cubed over 6 plus C3 times x plus C4. 4 conditions. But what can I do? Well, I'm going to write them here in a different color just so we can see them. So in this section, I know for sure that the displacement at x equals 0 is equal to 0. And I'll even number that. That's kind of condition 1. On this side, I know that the displacement at x equal L is 0. That's all I get from just my supports. Well, I only have 2 conditions, but I have four constants, so I need 2 more things. What other 2 things can I enforce? Well, let me think about this. If I calculate the slope using this equation, and the slope using this equation, they share a point. Where do they match? At L over 2, they should give the same slope? Yes, they should. Because your beam cannot have a dramatic change in slope. If it does that, it is deformed. And we're not doing deformed beams. So this is where it gets a little interesting. So what you're going to say is the slope from equation 1 at L over 2 should equal the slope from equation 2 at L over 2. Well, that would be a 3rd condition. What's a 4th condition? Well, what about the displacement?
Displacement at A and B.
Well, when the 2 equations match in the middle at L over 2, do you get different values for displacement? No. So our 4th equation will be the displacement from 1 at x equal L over 2 should equal the displacement from equation 2 at x equal L over 2. 4 equations, or 4 conditions, 1, 2, 3, 4 constants. So you just have to solve that set of equations. See? Easy, right? It can be very tedious at this point. Now, see what happens when you do this, okay? If I applied equation 1, what do I get? So I come up here to, I made a mistake here. This should be 1, and this should be 2. So I go to equation 1, put x equals 0, 0, 0, what do I get? All I get is C2. Well, that wasn't so hard. What happens if I apply this one on this side? So the displacement at 2 at x equal L equals 0. Well, I have to go evaluate this thing at L. What's the problem with that? I keep both C3 and C4. So that becomes P over 2. This is L cubed over 2 minus L cubed over 6, which is 2L cubed over 6, which is a third. So this becomes L cubed over, what did I say? 3, plus C3L plus C4. Ugh. So all this will give me is a relationship between C3 and C4. It won't give me a value. You see how this is going? It's not going well. Watch what happens when I do equation, when I try to do number 3. So I'll evaluate this slope at L over 2. Right? Do I know C1? No. So I get P L squared, and that's 2, 4, 4 is 16 EI plus C1. That's this term. And then I go over here and get this one evaluated at L over 2. You can see we're going to have some fun here. So I get L squared over 2, L squared, 2, 4, 8. So this is a half minus an eighth. So that would be 3/8. And half of that would be 3/16, I think. I did that kind of quick. But the point is to show you that now I have another relationship in C1 and C3. I can't solve that yet. And then you could do the last one, which is going to be very painful. So I now evaluate this displacement curve at L over 2. The only thing I know is C2 is 0. So I get PL cubed. Let's see, that's 8. What's 8 times 12? That's 96? Plus C1 at L over 2. That's this thing. And that has to be equal to this thing at L over 2. Now this is going to be bad. So these are all L cubes. So I get half times half times half. So that's an 1/8 minus, let's see, 2, 4, 8, 8, oh, 4, wow, this is going to be a mess. I don't want to do this anymore.
Okay. You don't need it.
So you're going to get something PL cubed, and right now I'm just going to put whatever it is over EI plus C3L over 2 plus C4. So now I got 3 equations. I got this equation, I got this equation, and I got this equation. 3 equations and 3 unknowns. C1, C3, C4. Solve it.
42.
Yeah, 42. So you can see that a surprisingly simple problem can be very complicated. So direct integration works great. It gives you equations for everything. But it really, really works well when the load is continuous, and you can do it with one equation. When you start getting multiple sets, it gets very challenging. So this will not be the preferred method as we move forward to even simple problems like this. Now, to help you out on the exam, I'm not going to give you a problem and say just solve it. I'm going to say solve it using direct integration. So that problem will probably be set up to work well for direct integration. Some of the new techniques that we're going to learn, they have strengths and weaknesses. So you'll end up learning about 3 or 4 techniques. Every one of them has a strength and a weakness. So it's just like tools in your toolbox. I know it's a very old, used metaphor, people overused, but it's true. You look at the problem, you say, that problem needs a 16-ounce hammer. So go get your 16-ounce hammer. Don't go get a tack hammer. Don't go get a sledgehammer. Get the 16-ounce hammer. If you need to drive a screw, you can drive a screw with a sledgehammer. It works. It's not the most efficient way to do it. So all of the methods we talk about will work for every problem, but they work well for certain classes of problems, and that's what I want you guys to start thinking about as we move forward. So any other questions about this before I terminate it? By the way, I'm not solving this. If you did really want to solve this problem, I would jump back and use the condition that the slope at L over 2 is 0, and it falls apart very nicely there. But I want to show you if I shift this, if this is like L over 3 and this is like 2L over 3, then you don't have that anymore. You don't know where the slope in the center, where the beam, or not center, where the slope out in the beam is 0. So this is one of those problems. I wanted you to see it and kind of see the limitation, but outside of maybe one homework problem or 2, you won't have to deal with it. Okay? So definitely a disadvantage for this method. My computer has gone on, so I can't stop the video right now. Here we go. All right. We'll stop it.